Hi there, and welcome to our lecture on conservation of energy. This is Energy 3 of Unit 7. Our key ideas: how does energy change? What is the law of conservation of energy? How much work done by a machine is actually useful? Alright, so we're going to look at energy transformations to start with. So how does energy change? So energy readily changes from one form to another. Whether we want it to or not, it does. So, for example, here potential energy can become kinetic energy. So as a roller coaster car goes down a hill, potential energy changes to kinetic energy. Now let me just draw a little picture for you here. So we've got our roller coaster hill here, right? And at the top of the hill, right before the roller coaster car goes down over the edge, we've got maximum potential energy. So potential energy is the greatest at the top. And there's very little, if any, kinetic energy up here. So very small kinetic energy. Mostly potential. But then as the car or the roller coaster goes down the hill, this potential energy is going to be transformed into kinetic energy because the roller coaster car is moving. So here, just at the bottom, we've now got a large amount of kinetic energy and a very small amount of potential energy. And actually, we could probably go, if we're all the way at the bottom, we could probably go as far as saying that there's zero potential energy at the bottom and all or most kinetic energy. And then if the car was not moving at the top, we'd have maximum potential energy and very little or no kinetic energy. So those are two possibilities. Let's see if I've got some other examples here. So kinetic energy can become potential energy as well. So the kinetic energy of the roller coaster car at the bottom of a hill can do work to carry it up another hill. So we've got our maximum kinetic energy at the bottom. So this kinetic energy that's at the bottom of this hill can allow it to then move up the next hill. So it transfers from the kinetic then to potential. So it becomes potential energy from there. And we basically can call this mechanical energy. This can change from one form to another. Let me go back here for just a minute though. When we're talking about potential energy changing to kinetic energy, the roller coaster works as well. But if we were just to drop an object from the top of a building or top of anything, so let's say we've got our building here. We've got our object that we're getting ready to drop. So here at the top, before we drop it, we've got this very large amount of potential energy. And again, little or no kinetic energy. But then as the ball drops, our kinetic energy will end up increasing, and we'll end up with this very small to no potential energy once the ball reaches the bottom of our reference point. And then somewhere in the middle, we've got a balance between potential energy and kinetic energy. So we could say that there's some balance here where there is a relative similarity between the two. Alright, so graphing mechanical energy. So the bar graph shown here presents data with about a roller coaster. So what variables are plotted? We can see here we've got the location along the roller coaster, and then how much total mechanical energy is present. And then we've got these bars here where potential energy is the purple and then the kinetic energy is blue. So that's the information we're given here. So we can see as the roller coaster proceeds, our potential energy was maximum here, so we were probably at the top of a hill. And then as we move down the hill, say at location B, we're moving, but we still have potential, so we're not all the way to the bottom. Whereas at the bottom of the hill here, we don't have any potential energy, so we're probably at the bottom with maximum kinetic, and then here, we're probably going back up the other hill. So just kind of a way to look at this graph. Again, location is the variable on the x-axis, so here's our independent variable. And then we've got the mechanical energy on the y-axis, so we've got the kinetic and potential energy and how they relate. So the independent variable is the location, because the car's kinetic energy and potential energy are going to change depending on where they're at on the roller coaster. So they're going to change with location. So at the top of the hill, there's going to be a different value of kinetic to potential energy versus or compared to the bottom of the hill. So then the legend here, kinetic energy, potential energy, tells us the car's mechanical energy consists of both of those things, and then it can change. All right, so the law of conservation of energy is telling us that energy is not going to be created or destroyed. So the total amount of energy in the universe never changes, but it can change from one form to another. So when looking at kinetic and potential of the roller coaster here, we end up with the total amount of energy the same. Energy is measured in joules, so the total energy is the same, but then it being potential energy at the top of the hill and the maximum kinetic energy at the bottom, we're changing forms in that case, or the example of changing forms. So energy does not appear or disappear. So whenever the total energy in a system increases, it must be due to energy that enters the system from an external source. So here we're talking about systems and external source, sometimes called the environment. So basically a system, really quick, is just the area that we're focused on at a given point in time. So say just draw a box or a circle around two objects, and we can call this the system. Maybe these are two objects that are going to be colliding, or maybe they're already collided and they're bouncing off each other. Who knows? But whatever we're focused on is the system, and then everything outside that box or the circle here is the environment or external source. So just a quick note. Thermodynamics, it describes energy conservation. So for any system, the net change in energy equals the energy transferred as work and as heat. So whenever this energy is transferred, it can be easily observed by touching. Maybe it got warmer, so that would be an example of some energy transfer taking place because there's heat taking place. Or if an object does something, so it works, moves something some distance, then we've got a energy transfer taking place. This form of the law of energy conservation is called the first law of thermodynamics. So just a quick little tidbit of information there. So thermo is temperature, dynamics, so it's study of the temperature changes, temperature transfers. We can talk about systems being open, closed, or isolated. So if a system is open, energy and matter are able to exchange with the surroundings, whereas a closed system, energy but not matter may be exchanged. So maybe we've got a jar that's got a chemical reaction taking place. Well, the energy can be expelled through that jar through heat, and you can feel the heat being expelled. So there's an example of the energy being exchanged with the outside environment, but whatever's going on with that reaction besides the heat is going to be in that jar. And then we can talk about isolated systems, so neither energy nor matter can be exchanged in these cases. And obviously most real-world systems are going to be open, so it's hard to separate the environmental factors with the system. Alright, so we're going to talk about efficiency here. So this is our last topic, I believe. So how much of the work done by a machine is actually useful. So, and obviously only a portion of the work done by any machine is useful work. So in other words, work that the machine is designed or intended to do is going to be the useful work. Production of heat, or not completely producing what we want it to produce, would be not useful work. And again, not all the work done by a machine is useful. We have friction, which causes a increase in heat. Maybe the machine's just not very good at doing whatever work it's supposed to be doing. So, but friction primarily, the work output is going to be less than the work input. So we're going to put more work into something to get a smaller amount of output. So we call this efficiency, and this is just the ratio of these two items, useful work out to work in. And define efficiency as a quantity usually expressed as a percentage that measures the ratio of useful work output to work input. And we've got another equation. Efficiency equals useful work output divided by work input. We might also say times 100 if we wanted it to be a percent. We can put, and I'll just throw that on here really quick. And we can multiply by 100 because the work output is going to be smaller than work input, so we'll end up with a decimal. And times 100 will give us a percentage. So really quick, a sailor uses a rope and an old squeaky pulley to raise a sail. It weighs 140 newtons. He finds that he must do 180 joules of work on the rope to raise the sail by 1 meter. He does 140 joules of work on the sail. So what is the efficiency of the pulley? And we're going to express our answer as a percentage. So we know the work input is 180 joules. The work output is 140 joules. So what's our efficiency? So using efficiency equals useful work output divided by work input. And what we have here is our work output is 140 joules divided by 180. We do get a percentage. We have 0.78. But to express that as a percentage, we have to multiply this as by 100, which is basically the same as moving our decimal to the right 2 places to give us 78%. And thanks for listening.